Hello everyone. So let's understand today's POTD, which is to find if array can be sorted. So we are given an array, zero index array, and we can do any of the operations. Like we can do any number of operations in this uh, nums array. And but at the same time, what we can do is like we have to swap only the adjacent elements plus like we can swap adjacent elements only and only if they have the same number of set bits. So now let's first understand the example given to us here. So 8 has one set bit, 4 has one set bit, 2 has one set bit, 30 has 4 set bits, and 15 has one set bit. So how can we know how much set bit do they have? So for that, like we have to understand these examples. Like we have to know like how to convert a number to their binary representation. So this is how we convert get the binary representation of a number. If I have number 8, so I'll try to make 8 with this configuration. How can I make 8 if I have this as a set bit and others as 0? How can I make 4 if I have this as a set bit and others as 0? How can I make 2 if I have this as a set bit and others as 0, like this? How can I make 13? 16, 8 plus 2, 10. Okay, and then 4, 1, 5. So 16 plus 10, it's like 16 plus 10 is 26, and then we get 30. So that's how we get 30. So for that we should be have a set bit in 16 and 8 and 4 and 2 and no set bit at one place. So that's how we are going to get 30. 15, how can we get 15? If we set bits at 8, 4, 2 and 1, we'll get 15. So that's how we get these set bits. So after knowing the set bits of all the numbers which we have given, we can make any number of operations of swapping adjacent numbers and have to make this nums as sorted. So then we'll apply some algorithms and logic which we will think and then like solve this question. So in the first example, as we can see, is that 8, 4, 2 have the same number of set bits, which is 1, and 30 and 15 have same number of set bits. So we can swap only same number of set bit numbers together. So like I can swap 2 with 4, so I can get this 2 above and then 4 here, and then I can swap these two, like 2 and 4, and so like eventually I'll be able to make it sorted. And then I have to like place 15 here and 13, and I can do this because they both have the same number of set bits. But here we cannot do this in example 3, as you can see, because only 3 has a set bit of 2, others have a set bit of 1. But in order to make it sorted, what I have to do, I have to place this 2 at the first position, but I cannot swap, but I cannot place it here. Like I cannot do any operation to place it here because we cannot swap 3 with any of these numbers because they have one set bit and this is 3. So we have to return false for that. So how can we solve this question? Okay, so one logic which I can think is, first of all, is to find the number of set bits for all the numbers, and we can do this like very easily by converting the number into its binary representation, or like using some bit manipulation techniques to solve this. And after that we can leverage the idea of bubble sort here. So what bubble sort do is that it compares the adjacent elements, and this is what we have to do. We just have to compare the adjacent elements. We don't have to like compare first and last, first and third, like some, not nothing like this. We just have to compare the adjacent elements. So for that we can leverage the idea of bubble sort here. So that's what we are going to do. So I've written the code previously. Actually I have written this code by explaining the solution only, but actually the voice did not get recorded last time, so I have to show the code now only. I'm not writing it again. It's okay, I'll explain it. Okay, so what we are doing is, okay, so the thing given to us is this bool can short array, and a nums vector is given to us. So first of all we find the size of our nums, and then I'm making a vector in set bits in which I'll store the number of set bits in my in of every nums element. Like for 8, how many set bits it has, I'll store it in my set bit. For 4, how many set bit it has, I'll store it in my this add num. By calling this add num, I'll find the set bits and store it in the set bit. So here I'm calling this. So as you can see, what I'm doing is I'm iterating in the nums array, and for every element I'm taking every element. I've taken the element and I have a counter as 0, so I'll count the number of set bits in my num and then I'll increase my counter. So for first of all, for the num, like for the number which is given to me, I'll do an AND operation with it. Why I'm doing AND? So basically the bitwise AND is used to check if my last digit of the number is set or not. If it is set, I'll increase my counter. This is what we have to do. If it is set, it will give me 1 as answer, so I will increase my count. And if it is not set, it will give me an answer of 0, so I don't have to, so my counter will not get increased. Something plus 0 is something only. So count plus 0 will remain count, and after that I'll decrement my number, which is I'll right shift that. So imagine like how right shift thing is working. So if I have this number and if I had this 8 number, okay, first. So if I do that nums and 1, it means it will give me answer as 0 because it is not set bit, so it will give me answer 1. And after that I want to check for this number, okay. So if I do that right shift, what it will happen is my number will be shifted to one place left, one place to the right. So with the if I do right shift in this number, my number will become 100, okay. And again right shift will become 10, and then it will become 0, something like this, okay. And we will do this until my number is greater than 0. So it becomes greater than smaller than 0, it means the number is finished and will not do anything. So after I get the count, the whole count of the set bits in the number, I'll add that count to the set bits and I'll move to the next number. So with this I'll get all the set bits for every number. After that what I can do is, okay, I can do this before counting set bits also. Okay, so it's your choice. Do it before that. It's more optimized. But I've done it here. It's not wrong, but yeah, it's a good practice if you do it before only. So now I'm checking for key. That is my nums already sorted? If it is, then we don't have to sort it with the help of the set bits. It is already sorted, so we can just return true. Okay, because this is what we have to do, right? Find if array can be sorted. So if it is already sorted, we don't have to sort, so we'll just return true. Otherwise we'll call this function called can sort. My can sort is now going to sort the number of all the elements in the nums according to the set bits. So it is same as the like the bubble sort logic. It is same the bubble sort logic and just the extra logic which our question wants us to do. So I'm doing that only, simple bubble sort. I'm checking if my nums j is greater than nums of j plus 1. If it is, I'll swap them because I need my answer to be in increasing order, okay. It's not in decreasing order. So if the adjacent elements are in decreasing order and if they have the equal number of set bits, I'll just swap those numbers. So after that I'll again check if my nums get sorted. If my nums got sorted after doing this short technique, I'll return true. Otherwise that nums cannot be sorted and I'll just return false. So now let's run it. I know it's working fine, but I have to show you and just submit it. Yeah, it's submitted and it's working very fine. Now let's understand the space and time complexity. First, the space complexity. So as we can see that we are using the extra space of set bits, which is of size n. So the space complexity will be big O of n, and we are not using anything else, just this and some counters and all, so it doesn't count to the space complexity. So yeah, the space complexity will be big of n, and the time complexity is for sorting it, like for is sort it taking big of n, And for can sort, we are doing this binaries bubble sort it, so it is taking big of n square, and then this add num, this is taking like for every element we are checking for its binary representations set bit, right? So as in the question given to me, that nums of I can be mm, like 2 raised to the power 8 number, it like this much big number. Okay, so like for every number we are doing, it can be of 2 raised to the power 8 length, right? For every number, so for every number we are going till its length, but the thing is we are doing it but but like we are doing this operation for every number, so it is not decreasing number one by one, it is decreasing number in half each time. So it is logarithmic of 2 raised to the power 8. 2 raised to the power 8 can also be written as 2 raised 256. So it is the time complexity for this function, and log 256 can be written as 8. So n into 8 is eventually 8 only, like n only. So the time complexity is big of n plus big of n square, and for sorting big of n. This is the time complexity. So yeah, the whole question is done. Thank you so much for watching.